So let's use one example to illustrate that general principle. So let's say we want to minimize this particular function. So now our x is belonging to R2. Okay, we have x1 and x2. So in that case, again, if you take a look at this particular function, we would still be able to somehow do some analysis and see, oh, okay, the optimal solution is again at 0, 0. So if you cannot see it, then that's not a big deal. All you need to do is to do some kind of arrangements, and then it can be proved. So if you cannot do that, that's fine, because that's not the important part of this example. Just take it as given. So we want to somehow do some iterations and try to move toward 0, 0. Let's see whether we may do that. And before that, because later we need to do a lot of gradient, so let's first prepare it. Let's first get the functional form of gradient. So we're going to differentiate this function f with respect to x1, we get this. With respect to x2, we get that. Okay, so that's the gradient. So first, let's say we somehow start at 2, 3. So 2, 3 is here. Okay, and we may evaluate its functional value. So we plug in 2, 3 to f, we're going to get 10. So step 1 is that we want to get our gradient. So you plug in 2, 3 to your gradient, you get 4, 4. 4, 4 is here, right? So we move in the opposite direction, which is to the left bottom direction. So now we need to solve your A0. For A0, we pretty much solve this minimization problem. So this means we need to express the functional values along this direction as a function of A. How to do that? Well, your x0 is something you know. Your x0 is 2, 3. And then you minus A. And then your gradient at x0 is also something you know. It's 4, 4. Right? So if that's the case, then after you do this, you're going to get 2 minus A4, 4A, and 3 minus 4A. That's how you get this thing. And these two elements are the coordinates of x1 and x2 along your improving direction as a function of A. All right? So you may evaluate this particular point's objective value by plugging in 2 minus 4a and 3 minus 4a into the original function f. So you plug in that back to f again. Then you're going to do some arithmetics. You're going to say, oh, okay, so this is going to be 4 times 2 minus 4a squared minus 4 times 2 minus 4a times 3 minus 4a, okay? And then plus 2 times 3 minus 4a squared. And all of these are functions, is a function of a. So you do some arrangement, do some simplification, eventually you get this. And once you get this, you see that, oh, okay, this may be solved. We may get an optimal solution for A, okay? And that's 1/2. Maybe you want to ask, how may we solve this problem? Well, when this is a single one-dimensional problem, and you understand that your A squared has a positive term, then using your high school math, you know this is quadratic function. And it has an upward curvature because your A squared, the second order term, has a positive value. So if that's the case, all you need to do is some kind of first order derivatives, and then you're done with that one, okay? Or you may make it something like some your high school math techniques. It would be something like this. It would say, oh, okay, so this function would be 32 a minus 1/2 squared, and then with some constant terms, okay, because you have this and that. So pretty much this function again may be minimized at 1/2, okay? So that's still something you know how to do. As long as it's a one-dimensional function, it's not too difficult. In the worst case, you do a numerical search along this direction, and that's still fine. So you will get this one, and then we know how to move to our x1. Our x1 would be x0, which is this one, minus a0, which is 1/2, multiplied by the gradient, 4. Then the calculation leaves us to 0, 1. Okay, so that's pretty much the point here, according to our figure. And don't forget to take a look at your objective value. Your f of x1 now becomes 2, which is much better than the original 10. Alright, so along this direction, you move to the best you may do, and that's going to give you some improvements. So we evaluate the gradient at x1. So the gradient can be found as -4 and 4, and its norm is 4 square root of 2. So this is quite large, right? So maybe we should do further. So now we may do step 2. And if we do step 2 very quickly, we would see that, oh, okay, so our second gradient here is -4 and 4. So it's here. So we're going to move along the opposite direction. And then we now need to solve the next step size. So again, here we take x1, which is 0, 1, and the minus a times the gradient here. And the gradient here is, again, -4, 4, according to our calculation. All right? So this gives you this particular expression for the coordinates. And then you plug in that to f, you get this one. And again, you may solve it and get your a1 should be 1/10. This is the best you may do in this iteration. So you're going to take 1/10 as your value for a1 and then move for one iteration. That's how you move to your next point, which is 2/5 and 3/5. And you again get some improvement. You go from the height 2 to the height 2/5. You evaluate the norm. Again, the norm of your gradient f of x2 would be here. And for this particular value is going to be 4 times square root of 2 divided by 5. This is still somehow large. Okay, so this is not a very small number, so maybe we should go further. So if you do some more iterations, for example, if you go again from x2, maybe you want to do some exercise by yourself, and then you would see that you will move to your next point, which would be x3. So I'm not going to tell you what would be the values for x3, but I can give you a hint that for x3, your second coordinates would again be 0. You will still have a point that lie on the x2 coordinates. Okay, so maybe you want to try that by yourself, and then eventually you will see that you will keep doing all of this until you reach the point 0, 0.